Today I'll be showing you how to take the extracted data that was shown in the previous video and modeling it to the Antoine equation in Python. So brief overview, we take our LXML library and import HTML so we can parse the HTML document and get the data from it. We do that with the request and the NumPy libraries as well. So down here we take our URL and set it equal to this variable. We then take our request and then grab the URL and set it equal to DDB. And then to get it in a nice tree structure, we then set it equal to html.fromString ddb.content. So that takes all the content in the HTML document and puts it in a tree structure in strings. And so if we want to split up our data into temperature and pressure, we then set tstrings equals tree.xpath, and then we drill all the way down until we get to table data 1, where all of our temperature strings are, and we take all the text within it. And then we do the exact same thing for the pressure strings, except it's in table data 2, and we take all of the data within it. And since these aren't XPath, these are all strings. So we have our data equals np.array. We want to get a two-dimensional array with our first dimension being temperature and our second dimension being pressure. And then we want to convert those strings to floating points. And so we do that as .asType np.float64. And so that then converts to floating points rather than strings. And so our temperature is equal to our data array, and then our first dimension, which is our temperature, and then all the way to the end. And then for our pressure, we have pressure equals, and then because it's a logarithmic function, we then take the log 10 of it, but it's in kilopascals, so we then multiply the data by 1,000 in the second dimension, and we do that for every single data point. And from there, we then do our figure equals make subplots, so then we can model this data that we have extracted from the website. And we want to add a scatter. And so we set our x-axis equal to our temperature data and our y-axis equal to our pressure data. And we do this as markers because it's data points and we never want that to be anything other than markers or dots. And to show you what this would look like, and we'll run it. So as you can see here, these are all dots and these are all the data points from the website. And all of the intricacies of the graph are then placed in here, and this basically just labels our x-axis, our y-axis, the size of our graph, and the color of our markers, and the name of our data, which is just data in this case. And so from here we then define the model, and we have our parameters of A, B, C, and temperature, and then we return the Antoine equation, which is A minus B divided by temperature plus C. And for this we'll have to do initial guesses for A, B, and C when we want to later do our minimize. And we then have this array of X initial equals our three-dimensional array of A guess, B guess, and C guess. And then we define the square error with the arguments of X, temperature, and pressure. And so we want to model this, and we set that equal to our X initial, second one, and then our third one, and then our temperature. And then we want to return the sum squared error, which is Jack's NumPy, so jnp.sum, and then model, which is right here, minus our pressure, initial pressure, and then we square that. And then once we get that, we then want to minimize that, our square error. So we set our minimize function equal to some variable, which in this case is res for result, and we take our initial and then our extra arguments, which are used for our gradient and our numerical derivative. Our tolerance is 1 times 10 to the negative 10th. And so right here is our numerical derivative of minimizing the square error here. And then below this, we then have our temperature model, which is linspace, our first temperature point, and then our last temperature point. And there's 100 of these points. And so then we add the scatter plot of our t model on our x-axis, and then our y model is our minimize.x, and then temperature model. And we want this to be a line because this is the Antoine equation, and we're modeling our data from before into the Antoine equation. So when we press this, we run it, it will show us our data points and then how it fits compared to our Antoine equation. Thanks.